Good morning. I thought we'd jump straight in there today with modelling with differentiation, because when Jimmy Cliff gives it a break. Right, because this is actually the final differentiation lesson, and I know a fair few of you have probably been wondering, well, when is it going to start to have anything to do with real life, as Mr. Goldberg promised us at the beginning? Well, this is when we start to see that happening. You can think of dy over dx as a small change of y divided by a small change in x, and it's representing the rate of change of y with respect to x. If you replace your value of y and your value of x with variables that represent real life quantities, you can then use the derivative to model lots of different real life situations, as long as they involve rates of change, and there are loads of those that go on. We're going to do a couple of the sort of simpler ones today, and then I'm going to give you some questions to work through. So we're starting off with a sphere here, so you'd probably like to pause it and write it down if you haven't done already. But we're looking at the fact that as a radius increases, because the volume is linked to the radius cubed, that means that the bigger the radius gets, the more the volume is going to expand faster and faster. And this question is wanting to know, what is the rate of change of volume with respect to radius at the instant when the radius is 5 centimeters? So at that moment, how many centimeters cubed is it getting bigger for each centimeter that the radius is getting bigger? And in order to do that, we just start off by jotting down what our formula is, and then we're going to differentiate that. And because it's v that we've got, it'll be dv on the top divided by dr, and then we do what we would normally do. So we're going to multiply by 3, which will give us 4, and we're going to drop the power by 1, which will give us squared. And then all we have to do is substitute the radius value as being 5 centimeters. So that'll give us 4 times pi times 5 squared. Now 5 squared is 25. 25 times 4 is 100. So that's going to give us 100 pi. And if they wanted it exact, you could say it would be 100 pi centimeters cubed per centimeter. But if they wanted to through significant figures, you could say that's going to be 314, because 3.14 times 100, 314 centimeters cubed per centimeter. And that's it. Let's have a look at a slightly more complex problem now. This is another one to do with volume and also surface area. So if you want to jot this down, you can do it from the book if you like, on page 279. So we've got a large tank in the shape of a cuboid that's to be made from 54 square meters of sheet metal. It's got a horizontal base and no top. The tank's height is x meters, two opposite faces are squares. So before I try and do anything else, I'm going to make a little sketch of what I've got so I can think clearly about what I'm trying to do. So I've got the idea that the two opposite faces are squares, so I'm going to draw one square like that as the front of my cuboid. And then I'm just going to run up to there, there, and then I can see in the top, can't I? So it's going to look something like that. Now it says the height is x meters. So if that height is x meters, that width there must also be x. What I don't know is this length here, so I'm going to call that y. And if I did know what all of that was, how would I work out the area, the surface area that I've got? Well, I've got 5 different sides, haven't I, to my cuboid, and I might, just to make it even easier to think about, draw the net of it. So if that's one end, that's the bottom. I would then have one side there, and there's my other square end. And as all of these sort of 2 squares wide ones are x, then that's going to give me x squared there, x squared there. As all of these lengths are y, I'm going to have xy, xy and xy, which would all add up to give me 3xy, wouldn't it? So I could say that I've got 2x squared plus 3xy, and that is giving me 54. At this point, I'd normally sit back and think, right, so what's going on here? I want to try to get to this, the volume, and there's no y's in that volume. So I need to get rid of the y that's in there. And how can I do that? Well, I know that the volume of a cuboid is length times the width times the height. So in this case, it's going to be x squared times y. So I need to put my y into terms of x, which I can do if I rearrange this. So if I take 2x squared from both sides, first of all, I'm going to get 3xy is 54, take 2x squared, and then if I divide by 3x, I will get 54, take 2x squared all over 3x. And now I'm going to put that into what I had for my volume. So my volume is going to be x squared times 54, take 2x squared all over 3x. At this moment I might think I want to try and simplify some of this, so I'm going to say, well, that's the same as putting the x squared outside a bracket, isn't it? I'm going to split this into 2 fractions with 3x as their denominator. So that gives me that, and then think, right, what can I do to simplify these? Well, I can divide by 3 there, and 3 goes into 54 18 times. So that would be 18 over x. And then over here I can divide top and bottom by x. So that gives me minus 2x over 3. And then all I need to do is multiply both of these by x squared. And if I do that, I get 18x squared divided by x is 18x. And I get minus 2/3, and that x times by x squared is going to become x cubed, isn't it? And that is what we needed. So now we want to know what value of x is going to give us the best size for our tank. Given that x can vary, use differentiation to find the maximum minimum value of v. So this is where we start to really solve something. Descartes, the great French philosopher and mathematician, said that you could solve any problem in the world as long as you first defined it with algebra. And the tricky bit can be defining it with algebra, but this is where we start to see some of that in action. So we're going to differentiate. V equals 18x minus 2/3 x cubed, so that'll give us dv over dx. It's going to be equal to, well, the x goes down to, and we just lose the x, don't we, to get 18, and then if we multiply by 3 we're going to get minus 2x squared. And in order to get the maximum minimum value, we need to get it when the differential is equal to 0, don't we? So we want that to equal 0. Add 2x squared to both sides, and I'll get 18 equals 2x squared. Therefore 9 is equal to x squared, and x must equal plus or minus 3. Now it's nonsense to have a dimension of something in real space being a negative number, so therefore it's going to be 3. Was it meters? Yes, it was meters. And that's our maximum or minimum. Now if you think about it, this is a quadratic with a negative coefficient of x squared, so it's going to a negative, it's going to give us a sad face, isn't it? So that should be a maximum. But the third question we're going to get, and I'm just going to write this out as we're doing it, is to justify that the value we just found is a maximum. And I've just realized that I've made a mistake, because 3 meters is that, and we need a value of v, don't we? So in order to find that value of v, so I'll come back to that part C bit in a minute, I need to put what we've found there is that our tank has got 3 meters there and there, hasn't it? But we don't know what the volume of it yet is without going back into our volume equation. So to say what the volume is, I'm going to have to do 18 times 3 minus 2/3, 3 times 3 to the power of 3, which will give me 54 minus 27. 2/3 of 27 is 18. 54 take 18 is 36. So that would be 36 meters cubed, and that's my final answer, isn't it? And this question here was saying justify that the value of v that we found, 36 meters cubed, is a maximum. Now we've just drawn that, so I know from my knowledge of those quadratics that it is a maximum, but in order to justify it we use the second differential. So if I differentiate that, then 2 times negative 2 is minus 4, and the power drops to 1, minus 4x, and when x equals 3, minus 4 times 3 equals negative 12, which is negative. And if you get a negative result in the second differential, that means it's a maximum. Therefore, it is a maximum. If it had been a positive answer we'd got, it would have been a minimum, and if it was if it was 0, then it could have been either or even an inflection. Right, so what are we going to do next? We need a few examples. No, we don't. You've had your examples. What you need is some practice to do this. So this is exercise 12k, and the best thing to do to get into this is to do a few of them again, I'm afraid, folks. So I want you to do all of that exercise. Now the first few questions just get you into doing a bit of differentiation again, and then as you go down they start being problem solving, and then some exam style ones as well. Next week's homework, I'm not setting the homework this week, that should be Mr. Cooper. Next week's homework will be a load from the mixed exercise afterwards. If you get through this quickly and want to have a go at that, by all means do. Remember, come and ask me if you've got any questions, folks. Some of you are doing that great. There's still about half of you that I'm waiting for scores on your homework in, so if you could send that in, that would be marvellous. Alright everybody, see you tomorrow. Bye bye.